Hello and welcome to CAD Dimensions webinar on flow simulation, HVAC, and electronic cooling modules. My name is Franco Rotoli. I'm an applications engineer here at CAD Dimensions. Today we're going to be talking about the flow simulation add-on modules, both the HVAC and the electronics cooling modules. I'll do a quick demo of each one, and if you guys have any questions, give us a call when we're done. I'd like to start off by saying that the HVAC module and the electronics cooling module are add-ons to the flow simulation. You do need flow simulation first, and then you can purchase the add-on either separately or together, and they are licensed separately. So just keep that in mind as we're going through this, as these do not come with flow simulation. They are separate. That being said, they have a bunch of features that really help you get a more accurate result with your flow simulation. The HVAC module includes things like comfort parameters, the discrete ordinates or DO radiation model, enhanced tracer studies, and an expanded engineering database. Today we're going to be talking about the comfort parameters section of the HVAC module. Stay tuned for later webinars where we'll also discuss the discrete ordinates radiation model. So what are comfort parameters? Comfort parameters are listed here. You can see the predicted mean vote, predicted percentage dissatisfied or PPD, draft temperature, air diffusion performance index, contaminant removal effectiveness, local air quality index. These are all things that you would use when designing your HVAC system to make sure it's effective in doing what you want it to do. For our example, we're going to do a hospital room. You can see here we have a patient on the bed along with a caregiver, a family member, whatever, some hospital equipment, and we have our inlets, our outlets, and our ceiling lights, as well as a television. So obviously the HVAC system is going to be removing air. We also have an outlet on the patient's face where he or she is expelling some contaminated air. So maybe they're very sick, and we want to make sure our HVAC system effectively removes the contaminants from the patient's exhaled air. Also, we have the hospital equipment, the lights, the people in the room, the TV set. These things are all giving off heat. We also want to make sure that the ventilation is adequate in removing this heat and maintaining a comfortable environment in the room. So here we see how we're going to judge those criteria. The contaminant removal effectiveness, the CRE, is how we're going to judge obviously the contaminant removal, along with the local air quality index. To make sure that the ventilation is adequate in cooling the room, we're going to use the air diffusion performance index, the predicted mean vote, and the predicted percentage dissatisfied. So let's go ahead and get started on the demonstration. Okay, so here we have our hospital room. You can see it's an internal study that we ran, and let's just take a look at our boundary conditions before we start looking at the results. So under boundary conditions we have volume flow. This is our air inlet to the room. We have an outlet volume flow, so this is sucking the air out of the room. Environmental pressure, this is just another exit. Maybe this is just a regular vent out into the hallway or vent into the restroom, it looks like, or the closet. And finally, an inlet volume flow, as I mentioned before, of the expired air of the patient. We're going to consider this the contaminated air. We also have some heat sources, so we have the patient heat source of emitting about 81 watts. The caregiver, about 144 watts, because they're standing up and actually doing some work, so they're emitting a little bit more heat. The ceiling lights, 120 watts. TV set, and some hospital equipment. Okay, so all these things are contributing to the temperature into the room. The goals we have set up are just radiant temperature, operative temperature, average velocity of the air, and the volume fraction of the expired air, because that's one of the main things we're concerned about. We want to make sure that our ventilation system is adequately removing the contaminated air. Okay, if I take a look at the summary for this, you can see that it took approximately 4,800 seconds, or about an hour and a half to run. I did it with a rather large mesh, or coarse mesh, I should say, so that it ran a little bit faster. But obviously, you would want to refine your mesh in the areas of concern. If we take a look down at the end of our summary here, we also see the comfort parameters do get put into our summary, which is nice. So we can see them right away just as a bulk. The CRE is the contaminant removal effectiveness of the entire system. You can see that the contaminant removal effectiveness of the air is 1, which is right where you want to be. And the removal of the expired air, which is more important, is significantly higher. So the CRE, the higher the number, the better. If the number goes below 1, it's a very poor effectiveness. It doesn't have a good effectiveness of removing the air. All right, we'll take a little bit closer look at these results here with some cut plots and things like that. If I expand out our cut plots, I just have a temperature cut plot. Let's show that, just so we can see the temperature of the room as I move this back and forth. So we can see blue is about 69, 70 degrees, and the red is up near 100 degrees Fahrenheit. Obviously, there's nothing red other than right near the lights, right near our heat sources. Maybe a little bit of the TV is emitting some hot air, but really the average of the room looks to be about 74 degrees, maybe a little bit cooler, which is good. That's a comfortable environment to be in. If we take a look at our next plot, PPD, which is predicted percent dissatisfied, this again is an important one, especially for a hospital room. We want to make sure that we get the least amount of people dissatisfied, especially for patients that are trying to recover. And we can see that a lot of the room is blue. Right? I'm going to play this. I'm just going to hit play so that we can watch the animation go back and forth. So blue, obviously green near the heat sources, and some reds near the heat sources. But you're not going to be spending all your time that close to the lights or the TV screen anyway. So we see that the PPD for the room is actually pretty good. So the comfort of the room seems to be very good. So let's go ahead and we will hide this plot. And next is the PMV, which is predicted mean value. Predicted mean vote. This is basically whether people are going to feel hot or cold. This is going to range between -3 and 3. And our ultimate goal is to be around 0. Not too hot, not too cold. If anything, maybe a little bit above 0, because I'd rather be a little bit warm in a hospital room than too cold. And you can see that that's I'm going to do the same thing here. I'm going to play this. We can see that that's about where we are. Mostly greens and a little bit of yellow. Really not a ton of blue, so it's not too cold in this room. Obviously, near the electronic equipment, once it comes back near the TV, we can see that there's some red, and around the lights there's red. But again, you're not going to be spending any time near there. So, predicted mean vote, I think that's hitting our goals. So far as a temperature goes, our HVAC system is being effective in keeping the room at a comfortable temperature. Next, the LAQI, the lackey of the expired air. So again, the LAQI is local air quality index, where 1 is perfect mixing of the air, of two fluids, I should say, excuse me. And the higher the number, the more effective the removal is. So again, we are showing the LAQI of the expired air. So this is essentially how much expired air is mixed in with the regular air in here. And I'm going to play this as well, just so we can watch it go back and forth. Obviously, we want higher numbers in our inlet area over here. Obviously, it's going to be a high number because there's no expired air in that region. So the more red we see, especially around floor level, or 4 or 5 feet up off the ground, that's good. That means that the expired air is being drawn up by the HVAC system and away from other people, so other people don't get infected. Probably one of the best spots to see that is over here. You can see that the the greens and the yellows, right, they're actually moving up towards the ventilation system, up towards the outlet. And I guess you can see that right there too, where the expired air is actually being drawn into the outlet. Remember, this is the inlet here, and this is the outlet over here that's actually sucking air out of the room. Okay, so just like everything else in flow, I mean, you can really do as many cut plots as you want. We can do surface plots of any surfaces in the room. We can take temperatures or any of the comfort parameters in here. We can do that very, very easily. Just to set one up real quick, if I insert a cut plot, we can see here we have our comfort parameters, draft temperature. Basically what this does is it tells you, it's almost like a wind chill, if you will, for HVAC. And we'll just set that up real quick and change the scale here. Okay, so again, this we want as close to 1 or 0 as possible. And we can see here 0 would be, or 1 would be about the yellow. So we see here that we're actually pretty good. In most of the active area of the room, we're doing pretty good. There's not a lot of air movement that you can feel at eye level or shoulder level, which is good. I mean, you don't want to feel a draft in the room as you're walking through. You don't want to feel the HVAC system. That's kind of the goal. All right. I'm going to hide these two. I also have an Isosurface Plot, which basically gives us the predicted mean value, or excuse me, predicted mean vote throughout the room. This is just another way to visualize what if I'm walking through this room, what I would be feeling. So we can see here that the predicted mean vote, there's a lot of yellow and a lot of green. So we're hovering between 0 and about 1. Which is good. That's exactly where you want to be. It's a little bit warm, but again, I'd rather be a little bit warm than a little bit cold. And we can also adjust our inlet temperature if we need to, basically to cool the room down if we decided that's what we wanted to do. Okay. Finally, we do have some volume parameters. What we did here was I extruded a block in this room, so I would get a volume, and what the volume parameters does is it gives us an average throughout the course of the volume. You can see it here. If I take a look at that, we can export this to Excel as well, but we're looking at the operative temperature, which is the average temperature of the room, the predicted mean vote, as well as the predicted percentage dissatisfied, as well as the local air quality index of the expired air. So if I show that, it takes a couple seconds to come up. Okay, so we see here that we get a minimum, maximum, and average for each one of these. Now remember, the operative temperature, the maximum, because I included the lights and all the hardware in the room, our maximum temperature is very high. I might want to reconsider what my volume is and really make it a little bit smaller so that it's in the effective area where a person would be standing or walking through. That would bring our average temperature down a little bit, because 74 is a little bit warm, but again, it's being thrown off by this maximum temperature of 540 degrees Fahrenheit, which obviously is very close to the lights and very close to the equipment, where you really wouldn't be standing anyway. The average predicted mean vote is right around 0.75, which again is verified by the plots that we showed. Again, same idea. The highest predicted mean vote is 701 because the cube that I made was so large, and it encompassed that high temperature. Obviously, no one wants to be in 700, or no one wants to be at 540 degree temperature, which throws up your predicted mean vote. So again, making that cube a little bit smaller, a little bit more realistic, it would give me a number that's probably a little bit closer to 0, which is exactly where we want to be. Remember, because the predicted mean vote goes from -3 to 3, -3 being very cold, and +3 being very hot. But even with this here, we're actually pretty good. We're at about 1, which is a little bit warm. Predicted percentage dissatisfied, average about 17. Again, this high temperature number is throwing these numbers off. So in reality, I would take a little bit closer look at that. And this is the good one, the local air quality index of the expired air. And we saw this with my cut plot, but we have an average of about 2.43, and that's going from 0 to 18,000, where the higher the number, the more effective the removal rate. So 2.43 is actually very good. That's a decent number to have. Maybe I want to move a little bit more air to get that contaminant out, obviously depending on how sick the patient actually is. If it's just a cold, then I may not want to tweak my HVAC system too much. But if it's something that's much more contagious and much worse, then I probably want to get that number a little bit higher. And of course, just like everything else in Flow, you can export this to Excel, so you can play with the data, and you can have the data outside of simulation Flow. All right, so that's just a very, very basic overview of our HVAC module and the comfort parameters and what they mean. Everything that I've gone through here, actually, you have in your, if you have Flow, you have it in your Flow installation directory. This is just a hospital room tutorial. If you go to your Flow simulation installation directory, Lang English Docs, then there's 3 documents in there: Solving Engineering Problems, Technical Reference, and Tutorial. So if you want to read more about any of these, I'm grabbing the models from in here under Examples. You can see the hospital room is right here. But more importantly, if you want to read more about any one of these comfort parameters, under Lang English Docs, there's a Technical Reference PDF. Let me call that up real quick. And we can see here that under HVAC, this gives you all the formulas that it's using to find for tracer studies, for local mean age, and the comfort parameters, which is what we've been talking about. It gives us the formulas for all those, as well as the predicted mean vote range, which we just talked about. You can see that the formulas are quite in depth. I'm not going to bore you by reading these to you, but obviously you can see that there's a lot of input that goes to these formulas, so they are in fact accurate. All right, so again, just to recap, this is in your Flow Simulation Installation Directory, Lang English Docs. Okay, and these are for all Flow users. Anyone who has Flow installed has these documents, as well as these example files. Okay, so now we're going to jump into the electronics cooling module. The electronics cooling module consists of a set of tools like 2 resistor components, joule heating, heat pipe model, PCB generator, and an expanded engineering database with more fans, more 2 resistor components, things like that, more PCBs. Today we're going to be discussing mostly 2 resistor components, heat pipes, and the PCB generator. While we do that, we will also touch on the engineering database expansion and increased information in the engineering database. The first thing I want to talk about is the 2 resistor component. The 2 resistor component, if any of you have taken a Flow simulation class, you know that whenever we represent a chip on a circuit board, for example, it's just one solid body, and we give it a wattage, and that's it, and then we look at the heat dissipation. The 2 resistor component allows us to much more accurately represent what is actually going on. It's a 2-piece model, and you model it as 2 chips mounted on top of one another. But in Flow, with the electronics cooling module, you specify the case and the junction. You can see that in blue and red here, as well as the junction to case and junction to board thermal resistances. We'll talk about that once we jump into SolidWorks. I'll show you that, and I'll show you how to specify that. The enhanced engineering database has a ton of packages that are already created for us, but I'll show you how to create a new one once we get to that point. So for our problem statement, we have a computer, simplified computer, of course, with a few chipsets, some RAM, and some other associated peripherals. But the objective is to make sure that the electronic components, mainly the chips and the RAM chips, do not exceed their operating temperatures. And you can see that right here. The CPU in this area, 85C, Northbridge, which is this one, 80C, Southbridge, 100C, and the RAM chips underneath, we don't want those to exceed 85C. And in reality, we want them to be even less, because these are the maximum operating temperatures. So let's go ahead and jump into the computer case demonstration. I'm just going to hop over to SOLIDWORKS here. And we can see our model here like we saw in the picture. I have a simplified configuration because, remember, with simulation you always want to simplify as much as you possibly can. Alright, so let's take a look at the setup of this model. It's set up in a very similar fashion to every other flow simulation, where you specify this, especially when you're dealing with heat conduction in solids, you specify the materials. In this case, the big PCB board is just a standard 8-layer PCB. The heat sink is copper, and the case is an insulator, and these are just a custom material. Boundary conditions, we just set up environmental pressure on the inlet, or on the inlets over here and underneath. And there's an external outlet fan that we specify over on this end. None of this information is new or unique to the electronics cooling module. We also set up some contact resistances here. We will come back and talk about these contact resistances. I want to talk about the heat pipes first before we get into that. Next is the perforated plates. So we specify perforated plates for the outlets. And I'd like to jump in first to my 2 resistor components. All right, so we see here we have 7 2 resistor components from CPU, the 2 chipsets that we mentioned earlier, and the 4 RAM chips that are on the bottom. Let's talk about how to set these up. If I just edit the definition of one of these, you can see here that basically what you do is you pick the case body and then the junction body. So that's important to note. If I section this model to here, we'll take the CPU for example. We can see that we have 2 actual components in here, one for the junction and one for the case. And you have to make sure that you pick the correct one. All right, so we see the case and the junction. Now, in our engineering database, if I jump into that real quick, we can see that under 2 resistor components, there are quite a few of predefined 2 resistor components. And let's just take a look. This one is the 35 by 35 2R. Let's just take a look at the item properties. You can see that it has a width and a length, so the size of the chipset, which is important for the conduction, and the case thickness, the junction thickness, which happen to be the same, and then the junction case thermal resistance and the junction to board thermal resistance. This is where the accuracy comes in, where if these were modeled as one just solid block, then we obviously couldn't put this in. So you can, in fact, create a user-defined 2 resistor component the same way as you create any other material. Then at the bottom here we put in a heat source. This CPU is going to generate 12 watts, and we're good. We repeated this again 7 times. One for the CPU, Northbridge, Southbridge, and then the RAM chips on the bottom. Moving down the list, our heat pipes. Heat pipes are essentially a high thermal conductivity, low thermal resistance mover of heat, if you will. And to set these up, basically we model them in a solid, and we specify the component. So this is one single component, and it goes into the heat sink. We specify the heat in face or faces, So this is the junction between the chip and the heat pipe, and we specify the heat out faces. So the heat where the heat exits the heat pipe, and obviously that's the junction between the heat sink and our